Hello everyone, this is section 1.2 on the language of sets. So first, what is a set? So by a set, we define what is a collection of elements or objects that we put together. We have a couple of different presentations for a set. It can be represented as a Venn diagram with circles, or it can be represented between brackets. And often when we're doing that, one of the important things is we want to know when there's an element that belongs to the set. So we use this notation that we have over here. We have this symbol A belongs to A, or this also means A is an element of the set A. In opposition, we also have that A does not belong to A, or that means that A is not an element of the set A. Um, in terms of representation, a set can be represented in a couple of ways. The first way to represent is going to be by extension, and a set is completely determined by this element, not by order or by repetition. So, for example, we can represent a set here. We have the set of 1, 2, 3, and this is going to be the same as we have the set of 3 to 1. Since they have the same elements, the order doesn't matter. Also, repetition doesn't matter. So we have 1, 1, 2, 3. This is still equivalent to the set 1, 2, 3. Repetition doesn't matter either. Now, we have some important sets in mathematics. We have the natural numbers that start from 1, 2, 3, 4 onwards. We have the integers that include all the positive naturals, all the negative natural numbers, and 0. We have the rational numbers, which are the fractions, or anything of the form p over q, where p is an integer and q is a natural. And we also have the real numbers, which are all the numbers on the real line or the number line. And this will include not only the rational, but the irrational numbers. So in terms of set notation, we have a couple ways that we can represent. We have the set roster notation, which is going to list elements between braces. So for example, between this and this. As an example, here we have the set of 1 to 3, which is defined as a set with 3 elements. We have 2, 4, 6, 8, and onwards, which is giving me all the positive even integers, although I don't seem to list them all. But the implication with these 3 dots is that this is going to continue giving me more and more of those even integers. We also have the empty set, which is represented by this symbol, or we can also represent it by the brackets with empty space inside. This will give me a set with no elements. It's very important to mention that the empty set is different from the 0. And for example, if we have the set with 0 inside, that's different from the number 0. A set is not a number. This is the set containing the number 0, and 0 is just a number. So we've got to clarify that in particular, we might have sets that don't necessarily have numbers as their elements, but they might have something else. They might have fruits or letters or words or many multiple things, since sets in particular are collections of elements. Now, that was roster notation, but we can also use set builder notation. And set builder notation describe elements by a property. So this will be given by something like this. We have the x's belongs to a certain set S so that they hold a property p of x. And so here, this can be mentioned as the set of all x in S such that property p of x is true. Some example of that will be the x that belong to the real numbers, so that x is bigger or equal than -1, but less than 3. That is essentially the real numbers between -1 and 3 without including 3 at the end. We also have changes depending on where the elements are coming. Notice that in the real numbers, this represents all the intervals minus 1 to 3. But if I change the initial set where these elements are coming, here we have the x that belong to C, b to minus 1 and 3. This means that I'm going to take all the integers between minus 1 and 3. And those integers are just going to be 0, 1, and 2. Notice that I don't include minus 1 and 3 because they're not included on the property. Okay. Now, subsets. Subset A is a subset of B and is written A subset of B if every element that is in A is also in B. So, for example, A equals 1, 2, or the set of 1, 2, is a subset of the set 1 to 3. Why? Because you can see every element that is in A, 1 is here, and it's also here, 2 is in A, and 2 is in B. Okay? In particular, A here is a subset of B, since every element of A is in B, but B is not in A. It's not a subset of A. Why? Because 3 is in B, but 3 is not in A. So that also gives me the other example, the example of when it's not a subset. Now, we have that A is a proper subset of B if I can, or written A subset of B, if you have that they're different. Like in this particular case, A is a proper subset of B. Now, the empty set contains no elements, but the empty set is going to be a subset for any other set. Also, a set is going to be a set of itself for any set. And it's very important to clarify that the empty set is not the same that the set of the empty set, because the empty set has 0 elements, but the set with the empty set is going to have 1 element, which is the empty set. Sets can also be seen as elements. Now, there's a key distinction that we need to make in symbology with sets, and is that this is the belong, and it relates to an element belonging to the sets, and this is the contain symbol, which relates to a set belonging to a set. So this means it's a subset of a set. So let's check a couple of examples. Here we have A, the set of 1 to 3. And so let's see if these statements are true. So first we have that 1 belongs to A, which is true because 1 is an element of A. Now the set of 1, the subset of 1 is a subset that is contained in A, and that is true. If you check, this is the element 1 is contained here, so this is a subset is contained in A. Now 1 is not a subset of A because 1 by itself is not a number. It's not a set. So being a number, it doesn't give me that it's a set, so it's not gonna be a subset. Now the set of 1 belonging to A is not valid because the set of 1 is not an element of A. And you can see it because it doesn't belong to the list. In particular here, when we're talking about lists, then it's easy to see when something belongs or not because you see it on the list. Sometimes we gotta check belonging by checking that A works with the property that the set has. Now let's check Cartesian products. So an ordered pair A, comma B in parentheses has 2 elements, and here the order matters. So it matters who's first. So the pair A parentheses A comma B is equals to the C comma D in between parentheses if and only if A is equals C and B is equals D. So this is only going to happen if they have these equalities. Now, order matters here. In sets, 2, 3 is the same as 3, 2, but in order pairs, 2, 3 is different from 3, 2. This is the first element, and it doesn't work if I flip the elements. Okay, so once again, the 1-2 order pair is different from the 2-1 order pair. Now, for Cartesian products, what we have is that we have the sets A and B, and we're going to take all the order pairs A and B, where A belongs to A and B belongs to B. Okay, and that's going to give me the set A times B of those order pairs. As an example, let's consider the 1, 2 and XY sets. This is the set A, this is the set B. So the A times B is going to be the combination 1x, 1y, that covers everything with ones. Now we do 2x and 2y, and then we do all the order pairs that are possible with the sets A and B. Notice that it has 4 elements, and this has 2 and 2. So you're going to realize that if the number of elements in A is m, and the order of elements in B is n, then the Cartesian product is going to have a number of elements m times n. Now, one key property here is because the nature of order pairs, A Cartesian product B is going to be different from B Cartesian product A. And we can check that once again with the 1, 2, xy sets as A and B. Notice that A times B starts with 1x, 1y, 2x, 2y, but B times A is going to be x1, x2, y1, y2. So the difference in the order of how they start make it so they're going to be different. Now, the Cartesian product is something that withstands 2 n-tuples. So we have the planes. So for example, R2, the Cartesian plane is R by R. R by R3, which is the 3-dimensional space, is just going to be R by R by R. So we can just extend this to n-tuples in general. It doesn't have to be just order pairs. We can make it with more elements involved. So as you can see here, for R3, we will have order triplets that will be X, Y, C, where each of the X, Y, and C belong to R. Okay, so this is, in summary, says our collections where order repetition don't matter. We have roster inbuilt notations that we can use. One is listing the elements, the other one is given me by a property. Subsets are sets that are going to be smaller parts or bigger sets. And as one set is a subset of another, means that every element of the initial set is in the other one. The empty set is in all the sets. And the Cartesian product is the set of order pairs with order matters. Now, let's go to another video with examples about this.